בריבוע פחות x בריבוע. זה הפורמולנט השלישי, x בשלישית, פחות 2x בריבוע x, ועוד x בשלישית, משהו כזה. ואני חושב שזה מה שהפורמולנט השלישי של תהליך חד-ממדי. אם הוא גאוסי, אז כל הפורמולנטים נוגעים, זה אתה יודע.
כן, אבל איך אתה מתרגם את זה טיים
זה פונקציה של הזמן.
כן, אז פה...
זה אותו דבר, כן, אז אני כאן לוקח את הכל עם אינדקס T. אני חושב, זה המומנט שני של תהליך הזמן. זה המומנט שלישי של תהליך הזמן.
כן, אוקיי.
אני שם את זה אחר כך. אנחנו קצת באיפה היום. Okay, good morning. I hope you are enjoying the holidays. חסרים לי פה כמה אנשים. So we started to talk about information measures. Which is actually a very big and very rich topic. So we're just talking about, at this point, Shannon information measures, and I just want to remind you what are the functions we're talking about. So we talked about the entropy of a random variable, which is essentially functional of the probability distribution of the variable, where we are still thinking about it as a discrete. So x can take only discrete values and actually even finite values, discrete and continuous and countable. And we just defined it as minus the expectation of the log of the probability. And we said that this quantity, which is called the entropy, actually has units. I mean, it has dimensions, and the units are determined by the base of the log. And if we take it to the log 2, then we measure these things in what we call bits, or binary units of information. Okay? Now, we are going to find more and more meanings to this function of the entropy. But at this point, so for a discrete random variable, this is a non-positive, a non-negative quantity, and it's always bounded by the log of the cardinality of x in that case. The number of elements, so when I say x is I think about it as the cardinality of the set, all the xi's that belong to x. So this is the number of elements that x can take, okay? So we are talking about finite cardinality. This is what I call the log n. So if this is n, this is log n, okay? So this is the maximum possible entropy. And this happens, and this is exactly the entropy of the equal probability, where all the elements have the same probability, okay? Uniform distribution. So this is, as I said, entropy is not an information measure, it's an uncertainty in X, okay? Yes, sure. Now, I'm just going to review it in a second, okay? Let me just remind you what I already said, and since there were people who were not in the on last week on Wednesday. I'm going to. So, and then we said, okay, entropy of one variable is very nice, but actually there's a very intuitive things which I want to call the condition entropy of one variable on another variable, which was simply the entropy, the average over x, over y in this case, of the entropy of the conditional distribution of x given y. So this in some sense is the minus sign, is the natural definition, is just the entropy. This is what you would call the entropy of x given some value of y. Because given this value of y, this has a distribution over x. But this, for a specific y, if I average over all the possible values of y, so this is just like averaging over y the conditional entropy of x. Sometimes we are just making explicit that the value of y is determined, is fixed to one instance. Okay, so this is and this is what we so this average is what we call the conditional entropy. Okay, I wrote it already. So this is the conditional entropy, or in conditional uncertainty, entropy of x given y. That's how we say it. Okay. And then we actually saw that this is nice because in some sense it's giving us the remaining uncertainty in x when I know y, or the remaining uncertainty. Of course, I can write the joint, the mutual entropy of two variables as in several ways. I can write it as the entropy in the variable x plus the residual entropy of x after, plus the residual entropy of y when I know x. And this, of course, is the same as the entropy of y plus the residual entropy of x when I know y. So this, of course, is just defined in the natural way. I just think of x as a two-dimensional variable. So this is just a minus sum over x and y of pxy log pxy. Okay, so this is the natural definition of an entropy for any random variable, and it factorizes in this way. So it tells us, actually, this is really nice because I can think about the uncertainty in two variables as the sum of the uncertainty in one of them plus the remaining uncertainty in the other one, given the fact that I already know x. So when I know x, I remove the uncertainty of x, and what's left is the uncertainty of y given x. Now, if x and y are independent, the conditional entropy of y is precisely the entropy of y, because this p of x given y is just p of x. Okay, so it doesn't change anything. So if they are independent, and only if they are independent, the entropy of the joint entropy, or the mutual entropy, is the sum of the two entropies. Okay. Yes. As far as I know, it's open, but as far as I can see, everything is open. But the podium is open, the computer is open. It should be all right. Yeah. Okay. Now, so this gave us actually some nice properties. So, for example, so we could actually draw it as some sort of a Venn diagram. So if I denote by the entropy of x the area of this circle, so this is x. So the area of this circle or ellipse is h of x, and this is y. So the area of this ellipse is h of y. So large entropy is large uncertainty, large area in this case. So the conditional entropy of x given y is the uncertainty remained in x when I know y. So if I know y, some of the uncertainty of x is removed. I mean, I have this byte of y in x. So this area, H, which is the area of the set x minus y, is just a condition entropy of x given y. And similar, this area is the condition entropy of y given x. Okay? And then it gives us this very natural leftover overlap. And this overlap between them is what we call the mutual information. So this is, don't take this Venn diagrams, by the way, too seriously. I mean, there's a lot of work on trying to justify them in higher dimensions than 2. It always gets very, very complicated. Because essentially you get, so even for 3 variables, this is already somewhat meaningless. I mean, it's not meaningless, but it can be positive. Things can be positive and negative, and the interpretation of area can be very dicey. Just like, you know, the how do you call it? How do you take the union expression of sets into there's a name in this in set theory. I mean, the expansion of a union of variables or union of set, or probability of a union as a sum of independent terms is actually extremely complicated. This is something which you usually don't like to do. So, but for 2 variables it works well, and we denote this area, which is completely symmetric in this case, as the mutual information, and we actually can see right away, and I denote it, as I said, by a semicolon here. So this is the mutual information between the variables x and y, mutual information, and or this is actually what we really would like to call information. So as I said, I mean, information is always in something about something else. It's a function of 2 entities. So you can't just talk about information in a variable. What do you mean by that? I mean, I can talk about the uncertainty of a variable, but I cannot talk about the information in a variable. It doesn't make sense unless you actually specify what is it that you want to know. If you want to know the value of the variable, then it's information about, it's some sort of self-mutual information. So indeed, age xx is actually age of x. But so this ixy is essentially, can be written in several ways just from this Venn diagram. For example, the uncertainty that is left in x when I know y. So it's the uncertainty of x minus the uncertainty removed by the knowledge of y, which is also the uncertainty of y minus the uncertainty of y when I know x. So this is just, you know, so it's the uncertainty of y minus this, or the uncertainty of x minus this. And it's also, of course, well, not of course, it's the uncertainty in x plus the uncertainty of y, which is the total area of these 2 circles, but minus, of course, the mutual uncertainty. So if they're independent, this is 0. Okay, so this is what we call mutual information. As I said, this is going to be an important function for everything we said so far. And of course, I can also write it as a KL divergence. Right, so IXY is also the KL divergence between the joint distribution and the product of the margin. Okay? So then this is trivial from this. But of course I can write it in 2 other ways. So it's the average KL divergence between Px given y and Px, or it's average over y in this case. It's also the average KL divergence of Py given x to Py, average over x in this case. So this corresponds to this, and this corresponds to this. So essentially it tells me, again, it's going to be 0 if the conditioning on y is not different from the unconditioned. So in some sense, it's telling me how much extra information you know about x when you have y, and the same is true, it's symmetrically true for this. Okay? And of course, you see immediately why it's true. Okay, so this is of course a non-negative quantity, which tells us something important. So since this is non-negative, it means that h of x is always greater or equal to h of x given y, which is what we usually say in information theory. We call it conditioning reduces entropy. So whatever you condition on, you cannot increase your entropy, only reduce it. Okay? Okay, but then I extended it further, and so essentially just taking this expression, Ixy is the entropy minus the conditional entropy on the other variable, or how much uncertainty is removed from x when I know y. I can define in the same way conditional mutual information. So the conditional mutual information, let's say I, x, y conditioned on some other variable z, is going to be naturally defined in that case. So what should it be? So it should be the entropy of x conditioned on z minus the conditional entropy of x conditioned on y and z. So I just do everything conditioned on z. So essentially, I want to know how much the conditional entropy of x, when I know z, how much of the entropy of x can I know is removed when I also know y. Okay? So this, again, it's a very intuitive, it's a very natural definition. And we actually saw that this is also, so this, by the way, can be both positive and negative. This is not obvious what the sign of this is. So this is actually interesting, because sometimes conditioning on something can increase the mutual information, and sometimes conditioning on something can reduce the mutual information. So it depends how they are related to each other. So, for example, we saw that, so this I can write, so this already suggests some sort of what we call the chain rule. So, yeah. So this rule, the fact that the mutual information, the entropy can be additive in when I add more variables, is actually the first step of what we call the chain rule of entropies. So essentially, it tells us, okay, entropy is additive when I add independent variables, and if they're not independent, if I condition on everything that I already know, I get an additive sum. So this suggests something which I wrote last time. So we have a chain rule for entropy, which is a very natural thing. So the entropy of a sequence of many variables, and of course we are interested in sequences of many variables all along. I mean, we really want to think about many observations, many random variables. So how is it broken? So again, this is just an extension of what I wrote before. So it's the uncertainty in the first variable plus the uncertainty in the second variable when I know the first variable, plus and so on, the uncertainty of the last variable when I know all the others. And I denote it by this. Okay? Just I lift the indexes, so this is all the sequences in Q. All right? Yes?
How can this be negative?
I'll talk about it in a second.
If conditioning already reduces entropy, then conditioning on y should.
Now, so unlike sorry, unlike entropy, which is actually always reduced by conditioning, information is not always reduced by conditioning.
So this is defined by the entropy.
Yes, but the difference of these two things, yeah. So it looks like I take the entropy and move some conditional entropy, but the relationship between x and y can be tricky, and that's exactly when we start to talk about Markov chains. So actually, this brings us to something which actually people use in neuroscience, which is called synergy of variables. So I don't know if you heard about it. So sometimes, for example, we see two neurons. and we want to relate the activity of two different neurons to, let's say, some action or some behavior or whatever, some stimuli. So I want to see if these two neurons actually tell me are synergistically increasing the information about the stimuli. Let's say I show you something, a face of someone, and I ask, is the information that this cell encodes about this face plus the information that this cell encodes actually giving me more information about the face or less information about the face? So it turns out that some neurons can be what we call synergistic. They act together, they increase the information. And some other neurons can actually give less information. When I see a neuron which is firing and another neuron which is not firing, or is firing because of something else, I can get negative, can get a reduction. So information can be reduced if I'm doing something which, sometimes we call it synergistic and redundant. So in some sense it can be anti-synergistic, in some sense, not really working for me. And actually we saw the first example of this when we talked about a Markov chain. So if x, y, z is a Markov chain, maybe before I talk about it, just remind, so we have a chain rule for entropies, and actually all these quantities are positive. There's no problem here. I just add non-negative entities, which are just conditional entropies, and all of them are positive. So this is simply breaking the uncertainty in a set of variables into some sentences. Of course, I can write n factorial different entities like this, okay? Because I can change the order of the variables any way I want, and I'll get a different entity, okay? So it's not just one. There are many chain rules like this, okay? Now, it becomes interesting if there are some sort of special dependencies of the variables. So for example, if there is a Markov chain here, so x2 depends only on x1, and x3 depends only on x2, and so on. So if I have a Markov chain, then what I know is that the entropy of x2 depends on x1, so this is important. But the entropy of x3 given x2 and x1 is what? Yeah, so it doesn't remember, it's not affected by x1 because everything that affects x3 goes through x2. That's the meaning of this Markov chain. So again, you can write it more formally by simply writing the Markov chain as a product. The probability of the distribution of a Markov chain is this, is px1 times px2 given x1. And in principle now I should write px3 given x2 and x1 and so on. But since it's a Markov chain, I depend only on the previous one, only on the one before me. So this is now px3 given x2 and so on up to pxn given xn minus 1. So you see the difference. This is only the last one, and this is all of them. Now, if it's a Markov chain, then this factorization is true. And then when I take the log, it breaks into the entropy of this, plus the conditional entropy of this and this, plus and so on. So it's only, so this equals to the conditional entropy of x3 given x2 in a Markov chain. Okay, so you see already that in a Markov chain, these things are very, very simple. They're only this chain rule is only related to the previous state of previous element. Now, okay, so this is nice because we're going to talk about the entropy of Markov chains. By the way, if it was a second order Markov chain, you know what it means. Second order means that each one depends only on the previous two. So then the same. This will still be 2 and 1, but from 3 on it will be only the previous two, and so on and so forth. So I can write this chain rule for any case order Markov chain in a very similar way.
Give this as example for why the initial information.
No, just a moment. So this is the chain rule for entropies. Now, what is the chain rule for information? So in principle, I should have something very similar, and indeed I have something very similar. So if I have a sequence of variables, and I want to ask how much mutual information is in the sequence about another variable y. So, by the way, unlike these things in entropies, which can grow forever, and in principle, I mean, these things can be all positive of the same order. So, if you talk about the entropy or the uncertainty of a long list of variables, even if they are Markovian of some finite order, this will grow eventually linearly in M. Because if I have a stationary sequence of things like this. So that's why we say the entropy is extensive. I mean, it's eventually going to grow linearly with the length of the system, the length of the chain in this case. So it's important. Maybe some of you have seen it otherwise. That's why entropy in physics is an extensive quantity. I mean, it scales like the volume or the number of particles or the energy of the system. They all scale with the size of the system. Information, on the other hand, is not, because this is bounded by information is always bounded by the entropy of the variables, each of them. So this is at most age of y. Now, if age of y is finite, and this will not grow, but I can still break it into some. So it's I, the information between x1 and y, plus the information between information between x2 and y given x1. Okay, this is still the natural thing. I mean, so now I can continue this in the same way. It should be plus the information between the last variable and y given all the previous one. Yeah, something like this. Okay, so this is a direct extension of this. And this is true. I mean, you can easily prove it from the chain rule that we already wrote about the mutual information. So if this is true, as I said, yeah, actually I want to write it like this. So, okay, so what I wrote here is true, but it's not general. I want to get to this inequality. So again, I can, so you see that it actually breaks into the components of the information that each variable is adding to on y. But now I know that everything here is bounded by the entropy of y. So it's this is some sort of a diminishing sequence. I mean, it cannot all contribute the same way. And indeed, I mean, if you add a lot of variables that tell you something about y, the entropy can only go down. And the mutual information cannot. These are independent components. So let's say y is binary. So if x1 is already giving me 1 bit, all these things should be either 0 or somehow with alternating signs or some funny things like this. And I get indeed that in this case the other information cannot be all positive or certainly not 1. So you already see from here that this either go down and converge to 1, let's say, in the entropy of y, or they can fluctuate in signs. They can do all sorts of funny things. Now, but this is still true. By the way, there is also, so this is a chain rule for information, or mutual information. And now also I have a chain rule for the DKL. So if I have, this is actually the basis of everything. If I have two distributions over some n variables, so I would like to factor it in a similar way. So what do you guess should happen here? So we already saw it actually, a simple version of this. So how would you guess the chain rule of the KL should look like? I mean, notice that the proofs of these things is essentially trivial. It's always the same idea. I factorize the probability distributions, and then the log breaks it into sums. That's it. There's nothing beyond that. So in this case, what would I do? I mean, I simply factorize these two distributions, for example, in that way. So px1 times px2 given x1 and so on, as before, and the same here, qx1 times qx2 given x1 and so on. So this is this factorization that I wrote before. But now when I put it in the log or in the KL, the log is going to break this product into sum. So what I should get, and I do get, is the KL between the first one. Okay? This is from this and this. Okay, plus the KL of the conditionals. Okay, so plus the KL of px2 given x1 to qx2 given x1, and so on. Plus eventually the KL between the last one, pxn given all the previous ones, to the last one here, qxn given the previous one. Okay, this is a bit dense here, but it's all right. So this is, again, I just proved it. Obvious. Okay. So this is a chain rule for the KL. And of course, if they are independent again, this is just going to scale with the sum of the decays. So you see that all these information measures have this nice additivity property, that independent events turn into sums of information. So that's why the DKL is actually a measure of information, because it's made out of entropies, and all the measure of information is actually made out of DKL. Yes?
Is there a simplified chain rule in case of Markov chain?
Yes, I'm going to talk about this now. Yeah, so this was just the definition of conditional information, and the chain rules actually tell me the following. Yeah.
I didn't see what's the connection between these two formulas. The DKL one and the anticipation one. What's the connection between these two formulas?
Between this and this?
Yeah.
So I can write information as a DKL, okay? Now, I can write it in various ways. I mean, so in this case, the information is going to be, so now both x and y are sequences, or one of them is a sequence and the other one is not a sequence. So for example, here I took a special case where x was a sequence and y was scalar, or one variable. Of course, I can also take y as a sequence, and then we're actually going to see this when we start talking about coding and the transmission of information, all these things. Then y is also going to be a sequence. And then I can ask what is the mutual information between a sequence and another sequence. This actually turned out to be an important quantity. This is precisely what we're going to see when we use channels, and then we use this is a key fundamental quantity information in communication theory, in channel theorem. But here, so okay, but now I plug it here. So again, the whole thing is just factorizing the distribution. So let's say in this case only x is a sequence and y is not a sequence. So this is going to be p of x1 to xn and y. And the same here, p of x1 and xn and py. And now you break this to factorize in x in exactly the same way. And once you get the factorization, the log is going to. So you can actually prove the chain rule of information from this. It's a very simple exercise. Do it yourself. Okay? Yes?
Please explain again how the information can be minimal, or what do you mean that it's bounded by information of y?
Because I see that IHXY is always HX minus HX minus 1, and this is positive. Both of them are positive. So everything here is bounded by edge of x.
But you have it n times.
No, and everything here is bounded by edge of y. So now I'm looking at the information in something about y. This is still age of y minus the conditional entropy of y given all the x's. So it's still bounded by the entropy of y.
If the second term here is 0, the
Yeah.
conditional information.
Yeah, if this is 0.
Yes.
Yeah, okay, so then the mutual information is precisely the entropy of y.
But n times.
Why n times?
Because each term here is
No, but it was here. So this is bounded by h of y.
I see.
So all these terms must also be bounded by h of y. So this can be either if all of them, let's say that the first one is already h of y, then all the others are either 0 or are with different signs. Otherwise, it doesn't work. And actually, the signs can change. That's precisely why conditional mutual information can be negative.
And maybe the intuition, but why it can be negative or maybe depending?
Yeah, so I'll give you intuition. Wow, it's taking me too long, but anyway, it's important. I just wanted to review what we did so far. So essentially, yes. What do you mean increase? No, it can increase, but it's bounded. I mean, it can be an increasing series. In this case, unless y is also, so for example, when you talk about the mutual information between a sequence, and let's say that y is also a sequence, then both of them increase, and then it can be extensive. I mean, this can be infinite. If y is also very complicated, I'm bounded by the entropy of both variables. So this can be very large, but this is bounded. So it's going to bound everything here. So again, this can happen if the sum of all these things is a all positive number which converges to 1, like half plus squared quarter and so on. Or it can be, they can have actually different signs, and then everything can happen. Okay? Now, we're actually going to see examples where this happens, but not now. So I just wanted to remind you. So, okay, so I have this chain rule. So if I have two variables, x and let's say x with respect to y and z. So the chain rule is telling me, so by the way, of course, the mutual information is a symmetric function. So ixy equals iyx. And so it doesn't matter. So everything that I say about one variable is also true about the other variable. Yeah, okay, so now I can write this as a chain rule, and I can write it as a chain rule in two ways. So this is not this. This is just definition of conditional entropy. But I can write it using the chain rule of information in two ways. So I can write it as ixy plus xz given y. So this is just using the chain rule to just wrote it for three variables. Okay? And so essentially, okay, so the information that x has on both y and z is the information that x has about y, plus the remaining information that x has about z given y. But I can also write it in the other way around. I mean, as ixz plus the conditional information of ixy given z. So this is just expanding this mutual information in two different ways in the chain rule of information. Okay? But now I look at the Markov chain. And I know that if there is a Markov chain, the information between z and x, or actually this one, xz given y, if I freeze y, x and z becomes independent. So in a Markov chain, condition on the middle variable is just like cutting the information between them. I don't allow, well, what I mean by this, I freeze y to one value, and then the changes in x are not going to affect anything, because z depends only on the value of y. So intuitively it's very clear, if in a Markov chain, if I freeze a variable in the middle, I disconnect the flow of information. There's no flow, guys. Okay, so remember this. So in this case, this ixz given y in the Markov chain is what? This is 0. And from that I got the nice inequality that ixy equals ixz plus something positive. No, I'm sorry. I confused you a little bit. Now this is still positive. I'm sorry if I confused you. This is still positive because of what you said, Hadass. So it's actually, this is still positive. What can be negative is when I start to condition on more than one variable, but this is strange. So this is still positive. And what I get from this is that ixy is greater than I xz. So everything that I said has to be revised now a little bit. Yeah, this is still positive because the entropy is reduced by conditioning, and what Haddad said actually was absolutely right. But if this is still positive, what I get from that is that the information along a Markov chain cannot increase, and this is what we call data processing inequality. Now I have to reiterate everything I said before in a correct way. So, so first of all, okay, this is true. This cannot be negative. What can be negative is what we call the synergy. So what can be negative is the difference between information and conditional information. So let me write it again. So again, I apologize for this. This is a stupid confusion. This is positive because, as I said, I mean, if I take entropy and condition on another thing, I cannot increase entropy. But this is because conditioning increases entropy and doesn't matter that they're all conditional, right? So this gives me the DPI. Okay, this is important. Okay, now what can be negative is what we call synergy, and let me just write it down once. So just as I took information to be the difference between entropy and conditional entropy, I can take something which sometimes we call synergy of x, y, and z to be the information between x and y minus. So remember, what I did in the definition of information, I took the entropy minus the conditional entropy. So now I want to take the information minus the conditional information. So this is minus the information of x and y conditioned on z. So this is sometimes we call it synergy. I think that it's double n, not one n. Synergy, double n. So this is a definition. You're going to find it in some, especially neuroscience papers, because we are really interested in synergy of neurons about stimuli or about actions. So this can be actually. So this is something which, in the Venn diagram, I can look at it like this. If this is x, and this is y, and this is z, the synergy is this. Okay? So essentially, it's the mutual information between x and y minus the information that is removed when I know z. It is left when I know z, sorry. So it's the information between x and y, which is this, minus the information that is left when I know z, which is this. And therefore, it's this area. So this synergy is here. Now, this can be of any sign. This can be both positive and negative. Okay? So this can be, first of all, just from the Venn diagram, you see that this can be written in various ways. It can be written as the information between x and z minus the conditional information of x and z given y. And it's also a combination between the information between y and z minus the mutual information between y and z given x. Okay, so all these three things are three different ways of writing it as this difference, or as this difference, or as this difference. Now, this funny thing, which we call the synergy of the variables x, y, and z, so it's a symmetric in some sense quantity. This can be any sign. It can be 0, can be positive, and can be negative.
So information is always positive?
Information is always positive because entropy and conditional entropy is always reduced. It's always true, and that was right before, and I'm really sorry that I got confused here. But But this is not this quantity, which is some sort of a conditional entropy, conditional image information. This is not necessarily positive. Okay. So remember this, and you already see that when you start to talk about more than 3 variables, you're going to have exponentially more interesting areas like this, all sorts of intersections. And this is going to be complicated. I mean, the signs of these things can be positive or negative or anything. That's what I meant by that. Okay, so indeed. So this series is still always positive. But as I said, I mean, it's bounded by the information. So it tells the entropy of y. So if, let's say, all the information is here, all the rest are 0. That's what it means. Yeah, and I'm sorry for this silly confusion, but at least gave us some interesting discussion. So I have to stop now. What I want to do next is to, so again, data processing inequality was an extremely important thing. I mean, so when I move along a Markov chain, information cannot grow. And it's actually due to the fact that conditional information is positive. But difference between information and conditional information is not necessarily positive, which means that conditional information can be higher than the mutual information. So conditioning does not reduce information, it can increase information. And to see this, so you see that in a Markov chain, conditioning on y reduces the information, brings it to 0. But if I have a different, say I have 3 variables, x, y, z, which are connected in some sort of a circular way. This is actually something which is not allowed because it's some sort of a. So in this case, okay, so let's say if z is related to both x and y, we know that knowing z is going to make the information between x and y 0. But knowing x can increase or decrease the information between z and y. We don't really know. So this is maybe if you ever take a course in what we call graphical models or probabilistic graphical models, or sometimes we call them Bayesian networks. There's actually a course. I mean, we used to have a course in computer science, an advanced course in machine learning, which was given by Gal Elidan or Yair or Amir or one of those. Or Nir Friedman. Actually, Nir Friedman has a very famous book together with Dastan Kohler on graphical models. And graphical models are essentially models which are described by graphs like this. So variables and conditioning and relationship between them. Every arrow is actually telling me that there is some connection. And now there is a full theory of very complicated graphical models. So for example, Markov chains are just a linear chain of variables like this. A hidden Markov model is a linear chain. So a hidden Markov model is a linear chain with x1, x2, and so on, with observations which looks like this. So we have a state in time, and we have observations. So this type of model is called a hidden Markov model, and so on and so forth. So there are models which are more and more complicated. And one of the things that we always know that if we think about it in terms of information can either increase or decrease when I know another variable. So there's a famous book on that, which goes to a famous guy called Yehuda Perl, who actually wrote the first really textbook on what's called Bayesian networks. And in his introduction to this book, he gives this funny example of alarm and rain and sprinkle. And actually, so there are 3 variables. Rain and sprinkles, and the grass was wet. Okay. Now the question is, was it raining tonight or last night? If I see the grass wet in the morning. Now I give you another variable that there was a sprinkler also in on my lawn. So of course the probability that there was rain, given that the sprinkler was off, is higher than the probability there was rain given the sprinkler was on. And so this type of connection between three variables can increase or decrease. If I'm giving you information about another variable, suddenly the information about the other one is very small. So for example, you don't know if it was raining, if the sprinkler was on. Maybe it was also raining. So the information in the fact that the grass was wet about the rain at night depends strongly on what I know about the other variable. It can be positive. It can have a very strong evidence for the rain at night if the sprinkler was off. And I have very little evidence if the sprinkler was on. No. So it doesn't. Sometimes it's actually can confuse you because you don't know anything. Just like in the Markov chain. The Markov chain, if you know why, X and Z don't tell you anything about it. So in some sense, the knowledge of Y is reducing the information between X and Z. But if you don't know why, there is more information. It's very funny.
But if you don't know that the sprinklers can be
Break already. Yeah. Okay. Yes.
even if you don't know that there are sprinklers that can be sprinklers.
No. So it's a little more complicated. But look just at the Markov chain. I think this is enough to convince you that things can be funny. If I don't know why, the measure information between X and Z is positive because there's some connection between them. I think they have to sum over all the values of Y that I don't know. But if I know Y, in this case, knowledge is actually reducing the information that to zero. And actually, with some slightly more complicated graphs, I can have negative information. And actually, I can have this difference between the information and the conditional information. Actually, I can have the conditional information is larger or smaller than the original information. And that's why synergy can be positive. Let's take a break. Okay. And I'm really, I had some very big confusion here, but I think that everything now is easy. לא, כשאתה מדברת על הקשרים בין דברים שונים, למשל, נניח אתה רפואה, ואת חושבת שהסימפטום הזה, את עושה דיאגנוז רפואי, ואת חושבת שסימפטום מסוים הוא אינדיקציה למחלה מסוימת. ועכשיו זאת אומרת, יש קורלציה חזקה לכאורה בין שני דברים שקורים, ואז פתאום אני אומר לך, בעצם היה משתנה שלישי שלא ידעת עליו, שגרם לשני הדברים ביחד. למשל, עישון וסרטן. אז אני יכול להגיד שאני רואה קורלציה מאוד חזקה בין סרטן ועישון. ואנחנו באמת מאמינים שסרטן עישון מסביר סרטן. באופן עקרוני יכול להיות מצב משתנה שלישי, שאומר לנו שאנשים שנמצאים סדר סרטן גם אוהבים לעשן. אבל זה לא שהעישון גרם לסרטן. זה פשוט יש משתנה שלישי, זה גן שגורם לשניהם לקרות ביחד. עכשיו, במקרה כזה, אתה לא יכולה להגיד שהעישון גורם לסרטן. כל הקשר האינפורמטיבי של התפיסת בין סרטן ועישון מותנה בהנחה שאין משתנה מתווך נוסף שיכול להסביר את שניהם. לא, אז אני אומר, יכול להיות שיש משתנה נוסף. אני רואה קשר בין X ו-Z, אבל בעצם הקשר הזה נוצר על ידי משתנה Y שלא ראיתי. עכשיו, במקרה כזה, המדידה של האינפורמציה משתנה בין X ו-Z היא מוטעת. זה משנה שזה לא נכון לשם שני. ואם אני רואה את המשנה השלישי, זה יכול להגדיל או אפילו להקטין את הקורלציה עצמם. או לאפס אותו,
אז נניח שהוא משתנה את זה.
הדוגמה שבדרך כלל מביאים בספרים, שאני לא רוצה להיכנס אליה, זו דוגמה של 4 משתנים. זאת אומרת שיש לי X, Y, ואז Z1 ו-Z2. ואני יודע ש-X משפיע על Y, אז X אני בכלל לא רואה, ואני עכשיו מודד באינפורמציה בין Z1 ו-Z2, ולפי המצב ש-X שלא ראיתי, אלה יכולים להיות יותר אינפורמטיביים או פחות אינפורמטיביים. ואני יכול לקבל דברים מאוד מוזרים בסוג הזה. זאת אומרת, שסינרגיה באמת יכולה לעלות. אבל בקיצור, אני אמרתי לך את זה בתור נתון כרגע, לא רוצה להיכנס לזה. הסיבה שאני אוהב להזכיר את זה, כי באמת אנחנו משתמשים במדדים האלה של סינרגיה בנורות. אז אם יש סצנה לא נכון, כל הזמן מאמרים ב-Nature ו-Science, אני חושב שזה לא נכון.
שמולה, הקונספט שמשתנה בנקה ברגרסיה?
סליחה?
ברגרסיה?
כן, גם ברגרסיה זה הכל רק שהנחות הן ליניאריות וגאוסיות, אבל זה אותו דבר. האינפורמציה הגאוסית יכולה לגדול אם יש משתנה שלישי או לקטון אם יש משתנה שלישי. זה תלוי מה המשתנה השלישי, איך הוא מנבא, איך פשוט משתנה שלישי. אז כן, אפשר להסתכל למשל, מספיק או z שווה איזשהו a1x ועוד a2y. עכשיו, במקרה כזה, אם אני לא יודע את y, אני רואה איזשהו קשר בין x ל-y, אבל בעצם כולו בא ממצב שונה של y שלא ראיתי. לכן, f משפיע על איך זה מקדם חיובי, זה מקדם שלילי, אז אני יכול לקבל כאילו קורלציה הפוכה מה שבאמת קורית כאן, כי היא באה ממצב שלא ראיתי. אז אפשר לראות הכל גם באנרגיה לינארית, רגע סינארית.
אז זה במקרה עכשיו על המצב שבו הסינרגיה שלילית, מתי היא תהיה חיובית, נגיד? סתם כדי שיהיה לי בראש.
סינרגיה חיובית זה מצב שבו את מקבלת אבידנס נוסף לאותה, נניח ראיתי. אז קליפות על דוגמאות שהסתכלנו עליהן בשפה. אני רואה את האות X, אבל אני יודע ש X נניח מדירה יותר באנגלית מאשר לעשות את זה. אבל בקונטקסט מסוים, אם אני לא יודע שאני נמצא בעצם, שהופיע עוד אות אחרת, באותו מילה, אז פתאום ההסתברות הזה יכולה להשתנות לגמרי. בקיצור, זה תמיד מצב שבו יש שלושה משתנים שהקשרים ביניהם לפעמים מסובכים. הגדרתי את זה ככה, זאת הגדרה, בסדר? אבל אני אומר לך, כרגע אני לא פרט יותר מזה, שזה יכול להיות חיובי, שלילי או אפס. ואני מבקש מכם בתור תרגיל, לחפש דוגמאות כאלה. אני אתן לכם דוגמה בנטפליקס, אני חושב שבנטפליקס בצורה יותר מסודרת. אני אתן להוריד לתת לכם תרגיל. שתתקנו בזה, בסדר? זה באמת סתם מבלבל. אבל זה בפירוש יכול להיות חיובי. את רואה, בגרף הזה את רואה שזה כאילו כמה אינפורמציה הוסרה, זה אנלוגיה לגמרי לאינפורמציה. ומכיוון שקונדישנינג מוריד אנטרופי, אבל קונדישנינג לא מוריד אינפורמציה. הטעות שלי הייתה שאני הלכתי עוד צורך יותר רחוק בתשובה שלי. קונדישנינג זה עדיין חיובי, אבל זה לא בהכרח מתנתת אותנו. קונדישנינג לא בהכרח מוריד אינפורמציה, יכול גם לעלות.
באינפורמציה בין x ל-y, ואני חושבת אתה יודע על y, רק
כן, תחשבי למשל ש-z מוסיף לי רעש על x ו-y. כשאני יודע את זה, הורדתי את הרעש. לא גם. אני רק רוצה לחדד מה שאמרתי קודם. תחשבי ש-x שווה ל-y פלוס z. ו-z הוא משתנה אקראי, רעש.
אוקיי.
ברור לנו במקרה כזה שאם אני יודע את הרעש, יש לי יותר אינפורמציה. אז במקרה כזה הרעש, האינפורמציה על Z, זה מקרה כזה עם סינרגיסט. ידיעה של Z נותנת לי...
זה תלוי בגרף שלך.
סליחה, במקרה כזה, ידיעה של הרעש, זאת אומרת, האינפורמציה בין X ל-Y, כשאני לא יודע את זה, תהיה יותר קטנה, האינפורמציה בין X ל-Y שאני כן יודע. נכון?
ברגע שתדע את זה, האינפורמציה כאילו מושלמת.
טוב, בסדר, אני חושב פה עוד איזה אלמנט של הרעש.
לא, בסדר.
זה לא חייב מושלם.
זה אידיאלי, אבל...
נכון, אז במקרה כזה זה יהיה יותר גדול מזה.
אבל זה שוב שלילי.
לא, זה יהיה יותר גדול מזה, וזה יהיה שלילי. הסינרגיה תהיה שלילי. אבל אפילו המקרה הפשוט הזה, ש-x הוא y ועוד z. z הוא שני קרי בלתי גדול y, זה רעש בלתי גדול. אז אני כבר אראה שהסינרגיה שלילי.
כן, זאת אומרת, הייתי חיובית נגיד, במקרה הזה יש דוגמה שתהיה חיובית?
כן, אם z הוא לא z, אם z קורלטיבי ל-y. אם z הוא איזשהו ay, עם a קטן, אז אני רואה את זה בגלל יותר. z מספר לי הרבה על y.
טוב, אנחנו מנסים ללחש את x.
כן, אני אומר, אז במקרה כזה ידיעה של z תחליש, כי אני מקבל פחות אינפורמציה. ואני הנחתי שזה הוא משתנה בלתי תלוי רעש, בלתי תלוי, אז אני אמרתי, לעשות איתי יותר, כי אני יודע את הרעש, יש לי יותר כאלה. אני משהו שאני לא יודע. זה היה דוגמה מאוד פשוטה כאן. אם זהו רעש בלתי תלוי.
נגיד אם זה שווה ל-y ממש, אז לדעת...
לא, אז אני רואה פעמיים את y, או אני רואה משהו ש...
אבל זה היה יותר קטן בגלל אם זה...
אז במקרה כזה, זה לא יוסיף לי אינפורמציה, אני חושב שזה יכול להיות יותר אפס.
אז זה יהיה אפס?
זאת אומרת, האינפורמציה הזאת תהיה כמו האינפורמציה הזאת, והסינרגיה תהיה.
תהיה חיובית. לא.
בכל מקרה, מה שרציתי זה דוגמה לסינרגיה שלילית.
לא, אוקיי, עכשיו זה חיובית, זה מה שהייתי בראש.
אז חיובית, תחשבי שאני מוסיף פה משתנה שהוא מאוד חזק, שהוא מאוד בלתי לא מספר לי.
בלתי תלוי מספר לי.
נכון, בלתי לא מספר לי. אומרת שיש לי כאילו מפרשרת מרקוב כזאת, ש-Z פה ו-X פה ו-Y פה, אז Z מספר על X עוד דבר ש-Y לא מספר.
אוקיי, ואז זה יהיה...
זה קצת מבלבל, אתה רוצה את זה אחרת, אבל זה כמעט משתמש בזהות הזאת. אבל כמעט שלושת הדברים האלה שווים. אז אני יכול לראות במקרה הזה שזה שיש לי, אם זה נותן לי עוד אינפורמציה ש-Y לא הייתה לי, אז אני אקבל כאילו, יש לך evidence אחד על X מ-Y, יש לך עוד evidence על X ב-Z. אז ברור שמקרה כזה, אני חושב שזה חיובי לא שלי, אז בנוירונים רואים הרבה דברים כאלה, אנחנו עושים כמה מאמרים על זה, על סינרגיה בנוירונים, לפני 20 שנה שעשינו נוירונים, עכשיו אנחנו רואים נוירונים שהם תראו למשל אחד הוא עושה אינבישן לשני, אני לא יודע את זה. אז אני מסתכל על קורלציה ביניהם ובין אירוע שלישי, חושב שאני רואה איזושהי גירוי בחוץ. אז אני אראה שכשאני לא רואה, כשאני יודע את הנוירון השישי, יש לי הרבה יותר אינפורמציה, כי אני יודע, אני אפילו מקפיל אותה, כשאני כן רואה את הנוירון השישי, האינפורמציה יורדת. זאת אומרת, אני לא מקפיל, אז קיצור כאן יש יותר אינפורמציה מכאן, זה בדיוק המקרה של הרעש. עכשיו, יכול להיות שזה לא אינביט אלקטריקט, ואז אני אקבל את אנרגיה כזאת. כלומר, זה באיזשהו מובן מפריד בין מקרים שמשתנה אחד כאילו מוריד לי את הפעילות של משתנה שני. אבל אני אתן לכם דוגמה מסודרת
שנייה, זה ממש יעזור.
כן, זה יעזור להבין את זה.
או אפילו בדרך כלל לי להבין איזה מקרים, כאילו...
כן, אז הדוגמה הקנונית היא דוגמה שזיהו רעש.
כן.
זאת אומרת, הוא לא מוסיף לי כלום, ואז אם אני יודע אותו, כאילו סילקתי את הרעש.
אני רוצה לו דוגמה להפוך.
אז אתה דוגמה להפוך, כן.
תודה רבה.
Okay, so I managed to confuse myself a little bit, but I hope you got out of it alive. So essentially, again, I just want to repeat. Conditional entropy, conditionally reduced entropy, conditional information is always positive, but it's not necessarily smaller than the original information. And I just want to give you this example. Let's say that x is y plus z, and z is just independent noise. So just a very simple relationship. I mean, there is a linear relationship between x and y, but z is noise. So in this case, the conditional information of x and y, given the noise, is larger than the information given between x and y without the noise. And this is going to be negative. And so think about it this way. Essentially, it depends if z is adding information or reducing information. And z can be compound to the other variables in a very complicated way. Okay, so this is an example where this can be negative. And there's a similar example that you're going to think about in an exercise where this is positive. Let's say if x is actually adding information, independent information. So let's say x is another letter in a language or something like this. So if z is noise, conditioning on it is a good idea. We remove the noise. If z is another piece of information, like two letters in text about a language, then conditioning it is going to eliminate information. Okay, so this is why this can be both positive and negative, but this on its own is positive. Yeah.
Wouldn't you want to reduce the information in this case?
Because if I know the noise, then x and y are very nicely related to each other. If I don't know the noise, so the condition is essentially assuming that you know it.
So I mean the other case, when z reduces.
Now, so let's say in x and z, y and z are two letters or two words in the language test that you did already. So each letter is giving you more information about the identity of the letter, unless they are equally likely in the 10 letters. In this case, conditioning on one is going to reduce the information that you have. It may reduce the information that you have another. But this is slightly more complicated. So I'm going to give you an example, I promise that, where you're going to clarify this thing completely. Where is synergy positive and where is synergy negative? So again, so this is essentially all I wanted to say about these things. But now I want to dive much deeper into the meaning of information, of entropy. So we already saw, everything is important, but I'll take this one. So we already saw that in some sense when we ask questions or we carry measurements, so you saw it very intuitively in this example of the 20 questions or the coin, the false coin or whatever, and you're going to see more of this. Just the branching axiom of entropy is giving us this notion that efficient measurements or efficient observations are those that maximize the entropy of the outcomes. Remember this? So for example, if you want to ask to play the 20 questions game, asking a binary question, yes, no question, which has maximum entropy of the outcomes, so the answer yes or no, are the most efficient questions or the most efficient measurements because they're going to reduce my uncertainty in the fastest way. That's how we got, for example, the number of questions, the number of answers that we need in recovering a number out of 100 is log 100 over log 2 and so on. Because log 2 was the maximum entropy. So you see that maximum entropy or maximum uncertainty in a measurement is actually something quite interesting. So this is the best type of observation that we can make. If a priori, before getting the answer, the entropy of the output is maximized. So this is the beginning of something which I'm going to expand just a little bit at this point, and we're going to get much deeper into this when we start talk about coding. So this type of measurement, I mean, building a set of questions to remove an uncertainty from a variable is actually a special case of what we're going to call source coding or noiseless source coding. Noiseless, so in the sense that I want to remove the uncertainty completely. So and then we are going to talk about lossy source coding. No. So this is essentially a beginning of something which I'm going to expand on Monday, which is what we call source coding or coding in general. So asking questions or making measurements are some sort of codes. And we're going to see this in a much more precise way. So, but there is also already a notion of what we call maximum entropy. Entropy Espen distributions. And it's not, I'm going to motivate it in two different ways. So first of all, so you already saw, I mean, that in some sense asking maximum entropy questions or making maximum entropy measurements is a good idea. I'm going to, as I said, entropy is intuitively, at least at this point, is a good measure of uncertainty in a variable, uncertainty in general. So maximum entropy looks like maximum uncertainty. Right? It's when I give it to a question, it's actually removing the maximum uncertainty. So that's why I want it to be maximized, because any answer is going to reduce the entropy maximally. Now, okay. But in general, I can ask, given a variable x, which has a distribution p of x, and let's say that what is the maximum entropy distribution subject to something? So we already know that if we don't know anything, the maximum of age of x, age of p of x, is exactly what we call log the cardinality of x. And this is the maximum I can do, and this happens when all the outcomes are equally likely. Okay, so maximum uncertainty is just intuitively maximum uncertainty. Everything is unknown. Now, what happens if I know something? I know something about x. So let's say, I'll give you an example of such a question. Let's say I have a die, yeah, what? With 6 edges, 1 to 6, and I'm telling you, okay, here it is. I didn't bring one with me, but you can imagine it. What is the probability of getting 6 in the next row? What would you say? Without knowing anything? Without knowing anything, you actually make a maximum entropy assumption, and tell me, okay, if I don't have any reason to doubt it, it's probably going to be 1 over 6. Okay, this is my best guess. Why? Because implicitly, you're actually maximizing the entropy, you're maximizing the uncertainty. You don't know anything. Okay, but now let's say I'm telling you, look, this particular die was, I actually threw it 1,000 times before the experiment, and I got that the average of the I, so xi in this case is 1 to up to 6, and so the average of xi was 4.5. I'm giving you this information. So my student did an experiment. They didn't tell me the details. I don't know exactly how many times each phase came up, but I am telling you that the average was 4.5. So so this is wrong. I mean, it should be how much? 3.5. And now I'm telling you, okay, this particular die that was average 4.5, what do you think is the probability of getting 6 now? Okay, so this is an ill-posed question. Right? This is an ill-posed question because there are 6 unknowns, P1 to P6. The only thing you know about them that they're in the simplex. So sum of a PI is 1, and they're positive, not negative. I'm giving you one equation. I'm giving you essentially this equation. The sum of IPI was 4.5. Okay? This is what I'm telling you. So you have 2 equations and 6 unknowns. You can't really determine P of 6. Okay? But let's say, you have to bet. You're a gambler, and what is your best estimate of P6? So of course, it can be that this particular die falls only on 4 and 5, equally. This will give you 4.5 exactly, and never on 6. But somehow you consider this is unlikely, for a reason which we'll try to clarify. So what would you do? So as I said, this is an ill-posed question. There's no principled answer to this question. But there's a very good reason to believe that just as you maximize the entropy when you didn't know anything, maybe you want to maximize the entropy subject to what you know. Okay? So the answer, or the reasonable answer to this, is take the argmax of age of p subject to this constraint, that some IPI was 4.5 and that some PI is 1. This is called the maximum entropy principle. Principle. And it's actually a very important practical tool, but very strangely motivated. So this is actually due to a guy called James in something like 1954 and 5 in two very famous papers. He actually motivated this principle as an inference principle. So if I have partial information about the distribution, so just like we had maximum likelihood. Maximum likelihood was the principle that then, okay, I want to find the most likely parameter given my data. That's essentially what it is, and it sounds okay, but we already saw that it's not always necessarily the best thing. If you are a Bayesian, you don't really want a maximum likelihood. You want something else. You want a distribution over your parameters, and each one of them can be anything. So this is not sort of a conjugate or something. It's entirely it's a method. So I want to maximize over all the distribution P, such that these two constraints are met. And in general, if I have more constraints, so in principle, if I know some partial, for example, if I know not only the first moment, this is the first moment of I, let's say I know also the sum of I squared pi and the sum of I cubed. If I have enough equations, eventually I'm going to determine my distribution. But in general, I have much fewer equations than variables. So there's a lot of freedom in my choice of distributions. And the maximum entropy is telling me, in this case, choose the one with the maximum entropy subject to your constraint. Now, what I'm going to tell you is actually very simple to prove. If you know something about Lagrange multipliers, and you should know. So if there are what we call expectation constraints, sometimes they call them moments constraints. Constraints. Something like this. So there are a1 of x up to a(r) of x, and this should remind. So let's say I have functions of x. In this case, the function was I itself, and I know the expectation. So I know these values. A1 with respect to p is something like a1, up to ar is something like ar. Which, and each one of these is just the sum over x of px ar of ak of x. Okay, where k can be anything between 1. So I have r constraints, and so these are what we call expectation constraints, or moments of the distribution. Now, what is the maximum entropy distribution subject to such constraints? So this is essentially the question. So the maximum, so the theorem, it's actually a very simple theorem. The maximum entropy distribution over x, which is the argmax of age of x, such that all this ar, ak, with respect to p equal ak, where k is any one of those constraints, is what? So can you guess what's going to happen here? So, okay, so the continuation of the theorem, what do you think it is? Yeah, so I don't know. I'll say it again. So again, so we are actually doing a maximization of a functional. So in this case, it's a function of the So again, I write it again. So the P maximum entropy, it's not me, it's maximum entropy, which is that distribution that maximizes age of P of x over all P's, such that, and we write it like this, AK of P is AK. And so this is a set of constraints. And of course, I also want sum of P to be 1. Okay, so I want to maximize the entropy in this set. So this is a set of possible distributions. Now, let me just give you an intuition again before. So P are points in a simplex. Okay, what is a simplex? So for example, if I have 3 possible outcomes, 1, 2, and 3, or x1, x2, and x3, then all the points that are summed to 1 are points in this rectangle. So you can think about this rectangle. This is the point 1, 0, 0. This is the point 0, 1, 0. And this is the point 0, 0, 1. So if I look at in 3-dimensional, this is in 3 dimensions. This is the probability of x1. This is the probability of x2. This is the probability of x3. So the simplex is a triangle that lies. It's a linear triangle that cuts the. Okay, so every point on this simplex corresponds to a distribution of 1, 2, and 3. Is this clear? So in general, we call this the simplex. In this case, it's 3 dimensions. So the 1-dimensional simplex is what? Just the 0, 1 interval. The 2-dimensional is this triangle. The 3-dimensional is a tetrahedra, actually, and so on. I mean, it's a cut of all the points which. So the dimensionality of the simplex is always the dimension of the number of L minus 1, and it's always bounded by the corner of this hypercube. Okay, so it's a convex set that connects the corners of the hypercube. In this case, these points. Okay. Okay, so how does the entropy function look in the simplex?
It's maximized at the center of mass.
Yeah. Okay. So we know it's maximum in the middle. So this middle is in this case third. Okay. And we know that it's actually 0 in the corners. So it's something. If I now draw a topographic map of the entropy, it looks like this, and so on. So this is a hill with maximum here, and the maximum is log n, is log 3 in this case, and it goes down, and eventually it is 0. So my drawing abilities are limited, but it's a kind of hill which. So it's 0 in this corner. It's a 2-dimensional entropy along each one of the edges, and it's end in the maximum here at log 2, and here at log 3. So it's kind of, you can think about a hill like this.
So the lines of the equal height are in the shape of a triangle, right?
No. So the close to the center, it actually looks more and more circular. When you push it towards the end, it looks more and more triangular. But actually, on each of these lines, it looks exactly like the 2-dimensional entropy. So the cross section here is a 2-dimensional entropy because the other variable is 0, and this is also true here. So it's 2-dimensional. This cross section looks like the 2-dimensional entropy, but here in the middle, I don't know how good you are in visualizing 3-dimensional things, but some of you certainly see this. Okay. So now I'm putting a constraint. So each of those constraints is a linear constraint in terms of the p's. It's a linear equation in the p's. Okay. So a linear equation will look like a hyperplane or a line that crosses this simplex. Okay? So let's say in my cube, or my die, it is essentially a line that crosses the 6-dimensional, the 5-dimensional, 6-dimensional simplex. So the maximum entropy is precisely the point on this line which is closest to the to the center, or which is tangent to the equi-entropy lines. This is the intuition of maximizing subject to constraints. So what is important for you to remember? So this point here is the maximum entropy point on this line.
But here, your constraints are not linear.
They're all linear because they all have this form.
So you assume this is the form of A?
Yeah. I assume they are my expectation constraints. Okay? So they are all linear in P.
But in general, A are P.
In general, the constraints can be nonlinear, but actually it's getting very, very complicated when the constraints. Linear in P, not in A. Not in X. So this can be any function of X, but it's linear in P. So these are linear equations in P. And if the A's are linearly independent, these are independent equations. So each one is actually reducing the dimensionality by exactly like an equation in just P dimensions. Okay, so this intuition that the maximum of such a constraint optimization is tangent to the line is precisely the intuition behind what we call Lagrange multipliers. So essentially it's telling me that at that point the gradient of the entropy should be orthogonal to the constraint. Okay? Because at this point the gradient should be just here. If it's not orthogonal, let's say it's here, then I can shift it until it's orthogonal and get to a higher point. So it's actually, more precisely, the gradient of the target function, in this case the entropy, should be orthogonal, should be a linear combination of the gradients of the constraint. This is the theorem of Lagrange multipliers, which I hope all of you saw somewhere. I'm not going to repeat it. So if you have constraints, so constraint optimization, essentially what it's telling me that this is equivalent to the argmax of what we call, sometimes called the Lagrangian of the problem, which is h of P minus some Lagrange multipliers over the gradient of the constraints, of the constraints. Some Pi or Px Arx.
Gradient or the?
No, so this is the Lagrangian.
Oh, and then you need to grab.
Lagrangian. If you haven't seen this name before, this is about time. So after Lagrange, of course, but it's so this particular, instead of writing in such that those constraints are met, I put the constraints here with Lagrange multiplier, with some constants, which I don't know. Essentially, what it's actually saying is that the gradient of the target function, the entropy in this case, is a linear combination of the constraints. That's what it means. Which is precisely this intuition that at this point you are orthogonal. So you're actually a linear combination of the gradient. The gradient of constraint is shifting the constraint a little bit in this direction. So it's a linear combination of the constraints. So this is called the method of Lagrange multipliers. And again, I'm not going to prove it. I just want to remind you this is what we do. Now, if this is the case, then it's actually very easy to solve this problem. So essentially, it's a convention that I'm going to use that the Lagrange multipliers I'm putting a minus sign here.
No, but the Lagrange multiplier should be should multiply the mean with the P minus what you want the mean to be, right?
Yes, but it's not important. So okay, yes, you're right. Remind you your name? Daniel, yeah. So this is of course the usual way, the standard comment when you do this. So okay, let me erase this. So yes, you are right. I just didn't have the space there. This is the argmax over P of this h of P minus sum of the constraints. Each one of them has a Lagrange multiplier lambda k, sorry. K go from 1 to r, so never mind. And then you write here actually the constraint itself, sum over x, p of x, a k of x, minus a k. Okay, that's what it should be. But as you see immediately, this doesn't matter. I mean, I can forget about it. Because the next thing I'm going to do is take a derivative. So how do we maximize the function, a multidimensional function?
That's really a derivative, right?
It's a functional derivative, never mind.
You need mean.
No, argmax. Because I want to maximize the entropy.
It's a dual problem.
No, it's not a dual problem. The direct, I want to maximize, so of course I also need to maximize with respect to the lambdas. Yeah, okay, so remember, so there's also a constraint which I didn't write, the normalization constraint. So I simply use the convention that a0 of x is simply 1. And by adding 0 here, I also added the normalization. Okay? So now I want to actually explicitly take the derivative. So this is minus some px, pxi, actually, just to make it clear that it is a discrete function of some dimensionality. Log pxi minus this sum over the constraints, lambda r, sum over xi, pxi minus, sorry, akxi minus this ak. Yeah, the sum is here. Okay? So now in order to maximize it or minimize it, doesn't matter, I take the derivative with respect to p and equate to 0. So I take actually the gradient. So this is what you call the Lagrangian. We often denote it by the letter L of p. Okay? For L for Lagrange. Okay? It's a bit confusing because it's not in different contexts. This Lagrangian has completely different meanings. And those of you who study mechanics, there's the other things there, but it's similar idea. So, okay, so this is just a notation for all these functions. So the beauty of the Lagrange multiplier method is that if I impose the constraints, I don't need to worry about them anymore. So now I can take independent derivatives with respect to all my variables. So essentially what I need to do is to take d to dp xi. So in this case, I treat pxi as one variable, one discrete variable, independently of this Lagrangian, and make it 0. And of course, there's an additional condition that I also need to satisfy, that d to the lambda of this Lagrangian is also 0. But this condition is precisely imposing the constraint. So, because the lambda appears only here, when I take the derivative, it's precisely that this is 0, which means the constraint is satisfied. So usually we don't really worry too much about this. We take this equation. Okay, so let's see what happens. It's actually very simple. So I now treat all the variables as independent, as if there are no constraints. So the derivative of p log p. So I take the respect to one of the i's. I have to do it with every one of the i's. So let's take one of them. That doesn't matter.
Why are the variables not independent?
Originally, they're not independent because they're constrained. I mean, they're supposed to satisfy, the sum should be 1. If the sum should be 1, and they're not independent. Right? I have equations on them. But once I impose using these Lagrange multipliers, I can write it down. So essentially, this is d, let's say due to dpi. So I just take the derivative with respect to this number, as if this is an independent variable. So the derivative of p log p, now it's actually convenient to think about it as ln. Doesn't matter, that's just a constant. So p ln p, the derivative of p ln p, what is it? So it's p, the derivative of ln, which is 1 over p. So this is 1. Plus ln p times the derivative, so it's 1 plus ln p. Okay? And that's simple. So I have the derivatives here are going to be pxi there's a minus here, so the minus pxi, I'm sorry, minus 1 minus ln pxi. So this is the only nonlinearity in the problem. The only thing which is nonlinear in p is this p ln p. Everything else is linear. So when I take derivative, I just get the constant. So plus or minus this sum of lambda r a lambda k, sorry, lambda k a k xi, which is just a number. I know this. And notice that the a, this little a that Daniel was worried about, doesn't show up here. So I don't worry about it. Okay? If you show it up only here, but this equation, I never really solved this equation. So this is just equivalent to those constraints that is being satisfied. So, okay, so that's what it is. This should be 0. Remember, this case gone from 0 to 1, 0 to r. So I can, this constant 1, I don't really worry about it. I can swallow it in lambda 0. Okay? So essentially, what is it? So forget about the 1 and just modify lambda 0 to include it. And what I get is that ln p is minus a sum of, or in other words, it's minus ln p here. So ln p is the sum minus the sum of lambda k a k of xi, where k goes from 1 to r, from 0 to r. This is what I get. What is it? This is our famous and familiar exponential forms, or pxi is just the exponent of this sum. Okay, that's with a minus sign. Never mind. So this is precisely telling me the log of the distribution is a linear function of my constraint, where the coefficients, those Lagrange multipliers, are actually what we used to think of as the parameter or the functions of the parameters in the exponential form. You see what happens? This is the solution to my derivative. So this leads to this. And you see that the log of the distribution, the ln of distribution, or the log, it doesn't matter, any log, is a linear combination of my constraints. But a linear, which means it's a sum of products of some functions which depends on, which I can think of as parameters, those lambdas, and functions of my data, which are the constraints. So this is actually justifying something I was throwing at you 2 or 3 weeks ago, that the exponential forms have maximum entropy subject to constraints. So the maximum entropy distributions are always exponential forms subject to my constraints. And we already know that these are precisely distributions for which those constraints are sufficient statistics. So in some sense, maximizing the entropy is like assuming that what I know about the distribution is sufficient in terms of sufficient conditions. It's actually going to be minimal sufficient statistics if these A's are linearly independent. Okay, so that's one important statement. Yes?
That term with the partition norm is used in the Lagrange, and if we fit the L2 norm, we might derive another linear result.
Why do you want the L2 norm?
I don't know. I'm asking why we put the L1 norm.
No. So I didn't have any norm here. I maximize the entropy subject to what I know.
Right.
And I told you that there's no other norm. Okay.
But you know, it's a difference between these two terms, between the norm of these two norms.
No, so you're saying something different. I mean, so you can, of course, say, okay, you want to get as close as possible to the linear constraint.
Right.
No, but actually I can satisfy the constraint. So the assumption is that there is a point in my simplex which actually satisfies all the constraints. If the constraints, by the way, are contradictory, and I cannot satisfy them, this is what we call an over-constraint problem. So this problem is under-constraint. I mean, usually I have less equations than unknowns, and I need another principle, which in this case is the maximum entropy principle, to find a distribution. You're talking about the other case where it's over-constrained. I have too many equations, which I cannot satisfy altogether. Then I'm an entirely different type of problem. Then I have to minimize the distance to my constraints. And this distance can be L2 or L1 or whatever. This is the over-constrained problem. In the least square problem, we actually have both of them. You can have an under-constraint, and then the least square is some sort of the minimum norm. Or it can be a maximum, an over-constrained problem. So when we talk about least mean square, in general, that's what you have in mind, I suppose. Then you really have to care about how well you can satisfy a constraint if they cannot be satisfied altogether. Here I explicitly assume that I have less constraint than I know. So there is, and the constraints are not contradictory. If they are linearly independent and there are less equations than unknown, I can always solve them. So what I just want to emphasize that suddenly the exponential forms have another meaning. They allowed us to have sufficient statistics. They achieved the Cramer-Rao inequality, if you remember, they were efficient. And they also maximized the entropy. Okay. Now I really want to give you the important part about entropy. Unfortunately, I'm out of time. Well, this was supposed to be, so I'm going to continue it on Monday, but I want to start now. So so far I gave you all sorts of technical reasons why entropy is interesting. I mean, so it obeyed the chain rule, it obeyed the branching axiom, it seems to be a reasonable measure of uncertainty, and so on and so forth. But all these are not the real reasons why this is such an important function. The real reasons come from the following identity, which I'm going to just begin now and continue on Monday. And this is really the most important discussion that I had so far in information theory. This is called typicality. Typical data or typical sequence. So we talk about sequences, we're actually going to talk about data in much more general form, or even whatever. Many things can be typical. So what do I mean by typicality? So there is something called, let me start before I formally define it, and I'll do it on Monday. The log of a probability of a long sequence of variables. So again, remember we are thinking about many observations. This is going to be the game we're going to play from now on. We're going to talk about many, many observations. We already did it. And we are going to think about what we call large typical problems. So if we have IID observations, let's say, so this log is essentially a sum of the probability is a product. In the case of IID observations,